So here is, again, the ions. Remember, the word ion means it has a charge. So AKA it's gaining or losing electrons, okay? Cations are positively charged, anions are negatively charged, so yes, you need to know that. So let's do neutral lithium. Neutral lithium, lithium has 3 protons, so it would have 1, 2, 3 electrons. 1, 2, 3 electrons. 1, 2, 3 electrons, okay? Now remember, the radius is defined as the nucleus, so here's my nucleus right in the center of the atom, all the way out to wherever there's outermost electrons. So that's this valence shell, right, out to the outer valence shell. This would be the size of the atom. Okay, now this is neutral lithium, so I called it the atom. Now, let's talk about a cation. +1 means you're losing 1 electron. Well, if you lose 1 electron, you're going to lose it from the outermost energy level first, okay? Because those electrons are further away from the nucleus, so they're not held as tightly. So -1. So I shouldn't say that. I removed 1 electron, so now this has become +1. But what does that do then? Well, that changes my radius, right? My radius only now goes out to here because now there's only electrons in this shell. There's no electrons in that second energy level. So the cation version of what's called, this is called like the parent atom, meaning it's like the original one. The cation's always going to be smaller than its parent, okay? Because you lose an electron, so the radii shrinks. So the cation is small. Now, for the anion means we're adding an extra electron. That's what the -1 means. And again, you're going to add it to the outermost energy level. Now, this is going to be conceptually a little bit harder to see, but this electron right here and this electron right here don't like each other. They repel each other. So when you add in an extra electron to this outermost shell that wasn't supposed to be there originally, the 2 electrons actually move a little bit away from each other. So they move a little bit further out. So now my radii, my atom, has electrons out here. That is because of electron repulsion. Electrons don't like to be next to other electrons, which causes the radii to increase a little bit because those 2 electrons don't want to be next to each other. So this anion has the largest radius of all of the 3. Okay. The notes should be on Canvas. It's on the notes always are on the home page. If you scroll down, all the different notes as well as my YouTubes. Okay, so if this says rank by increasing radii, remember increasing means smallest radii to largest radii. We're going to locate these 2 guys, so I'll pull up my periodic table. So we've got hydrogen and chlorine that we're comparing. Okay, so here's hydrogen, here's chlorine. Okay, hydrogen is on the first energy level. It only has 1 ring of electrons. So no matter what, its anion or cation is the small, one of those is the smallest. So if you go back here, is hydrogen or hydrogen cation smaller? Well, hydrogen, I'll do this over here, hydrogen cation is the smallest, and then hydrogen, because if hydrogen loses 1 electron, it doesn't even have electrons anymore. Okay, so the cation is always smaller than its parent, that's what we call it, atom. So now chlorine and chloride. So chlorine is obviously next, but now which one? Who's smaller, the chlorine or the chloride, and why? Anybody want to answer or try to answer? So we've got chlorine.
Chlorine.
And then chlorine -1. So chlorine is smaller. Why do you think so, Nathan?
Since not negative charge, and it comes like next after hydrogen?
Yep.
Next.
So you have chlorine. The reason it's chlorine and not chloride is because chloride's going to have one extra electron. An anion of the parent atom causes repulsion in the valence shell, which causes the electrons to move away from each other. If they're moving away, the atom or the radius is expanding. So the chloride anion, would be the largest. Any questions on the rankings? Good job, Sarah. I saw you sitting in the chat too. You got it right. Okay. So we are going. I want you to take a minute, and I'm gonna pause this. I'll start back up. I would like you to do A, B, C, and D. We're gonna go over E together. All right. So so we're trying to pick which one is the atom or the ion, which is larger. So if you notice A, B, C, or A and B, these are two of the same elements, okay? So there's like a parent atom and then an ion of the parent atom. So this guy is larger because it hasn't lost 2 electrons. When it loses 2 electrons, oh, sorry. So this guy is larger because it hasn't lost 2 electrons. So if it hasn't lost 2 electrons, it hasn't lost its valence shell, which makes this guy bigger. When this guy loses 2 electrons, it loses its outermost shell, so it causes it to shrink. Remember that the cation is always smaller than its parent neutral version. So they call this a parent atom. Okay, so now we have 2 of the same elements again, but one is an anion. So this guy is larger, right? Because those 2 extra electrons in the valence shell causes repulsion, and that will cause the electrons to move away from each other, therefore increasing the radii. Okay, now these 2 guys are not parents of each other because they're not the same thing. They are in the same family though. So if you go to your periodic table and you look up calcium and barium, this is going to be a lot easier. So look at calcium's here, barium is down here. Okay, it's going to be barium, but let's talk about why. When barium loses 2 electrons, it becomes isoelectronic with xenon. When calcium loses 2 electrons, it becomes isoelectronic with argon. Xenon is bigger than argon. Why? Because it's on the 5th period and argon is on the 3rd period. So this guy has 5 rings while this guy only has 3. Xenon would be bigger. So the barium ion, of which is isoelectronic with xenon is the larger of the 2. Okay? And this is going to be a similar concept with similar concept with the chloride, and the iodide. Okay, so Cl minus, when Cl gains 1, it's isoelectronic with argon. When iodine gains 1, it's isoelectronic with xenon. Okay, these down here have way more rings of electrons than these guys. So the iodide ion is the larger of the 2. Now, this is harder. Can anybody tell me what is special about these 2 cations? So I'm going to take a second and I'm going to draw them. Well, I'm going to try to draw them, I guess. So we'll have 1, 2, sorry, right? These are both on the 3rd energy level. 1, 2, 3. They're neutral. So I'm going to draw just sodium first. So just sodium and just aluminum. So now sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Aluminum has 13, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 electrons. Ooh, Hannah sent me a message and she got it right, but I'm gonna keep going. So look at, so this is neutral sodium, this is neutral aluminum. What does +1 mean? +1 means you lose one valence electron. So I'm gonna lose this one, right? Now, I don't have any electrons in this outermost shell anymore, so I'm gonna get rid of it. I don't have any electrons out there. Okay? Now, so this is now sodium cation, +1. Now, aluminum +3 means I have to get rid of 3 electrons. So you always remove from the valence shell first. 1, 2, 3. Now there's no electrons out here, right? So there's no valence shell here, meaning sodium ion and aluminum ion are isoelectronic. Isoelectronic with each other. Meaning they both have the same exact number of electrons. So, how do I figure out who is bigger and who is smaller? Does anybody want to guess? If it's not electrons, yes, good job, Sarah, you got it too. They're isoelectronic. If they're not, if they have the same number of electrons, it's not going to be electrons that play a role. So Natalie is saying sodium +1 is larger. So that's what she picks. And she is correct. Natalie, do you know how to explain why, or did you just get a good guess? Levi, did you raise? Oh, go ahead. Now, is that Natalie? Anyone can answer.
Way like more electrons, and that's why it's smaller.
Wait, who? Sorry, I couldn't hear you. I couldn't hear the first part. I think I cut you off.
Because you took away more electrons for the other one.
Okay, so it isn't. So this is kind of a hard concept. So we did recognize that they're isoelectronic, but there's something else we learned yesterday that causes the size of the atom to change. Levi, do you know what it is? Or do you want to guess?
Is it because since they both have the same amount of electrons that since sodium has a smaller nucleus, its radius is larger?
Okay, so I think this is what you're getting at. Sodium has 11 protons in its nucleus, while aluminum has 13 protons in its nucleus. We know that the more protons that you have in the nucleus, as long as you're on the same energy level, shrinks the atom because of the effective nuclear charge. The electrons become attracted to the nucleus. And so aluminum would be smaller because it has a higher effective nuclear charge, and it has a higher effective nuclear charge because it has more protons in its nucleus. So yes, they have the same number of electrons. Yes, they have the same number of rings of electrons, but they differ in the number of protons, which what makes sodium larger. Sodium cation is larger. Good job. So this was like a challenge one per E. Okay. All right, so here's all of our answers. Keep going. All right. The biggest struggle kids have in this chapter is remembering what definitions mean. So I don't like memorizing, but you just need to know what the word ionization energy means. The trend is not super difficult, but if you don't know what it means, then it is going to be difficult. Okay, so ionization, so right, ion is to have a charge, right? So ionization energy is the amount of energy required to rip off an electron of an atom. So you take some sort of atom, you put in energy, and you turn that atom into it loses a charge, right? And you remove an electron. If something has high, and then I'm going to start abbreviating ionization energy as IE, okay? Ionization energy. If something has high ionization energy, it means you have to put in a lot of energy to remove the electron, aka it's hard to remove the electron. If something has low ionization energy, it means it's easy to remove the electron. So there are first ionization energies. This is the amount of energy to rip off the first electron. This would be the amount of energy to rip off a second electron and a third electron and so forth. And so we'll do some practice. But before we practice, so I'm going to come back here. Okay. Oh shoot, sorry, the formatting's a little bit funky. There are trends, right? We're gonna move across a period and down a group, just like we did for radius. We went across a period and down a group. But I want to talk about the periodic table just without discussing the trends yet. So on your periodic table, you have a bunch of families, okay? So you have like your alkali metals. And then on the extreme opposite end, you have your noble gases. So let's just talk about this. Your noble gases, are they stable? Yes or no? Noble gases, stable?
Yes.
Yes, very stable. Which means, do they really like their valence electrons? Do they really want to hold tightly onto their valence electrons? So if they're really stable, they don't want to gain electrons, they don't want to lose electrons, they just want to be left alone. So these guys have really, really high ionization energy, meaning if you want to try to take an electron from a noble gas, you're going to have to put in a lot of work, okay? What about on the extreme other end, your alkali metals? How many valence electrons do your alkali metals have? All of these guys. I know hydrogen's not an alkali metal, but it's lumped here because they all have the same number of valence electrons. How many is it? 1. Good job. 1 valence electron. So how many electrons are they away from being stable? These guys all have 1 valence electron. They'd really, 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 really like to lose 1 electron to become stable, because like if potassium loses 1 electron, it's now isoelectronic with argon. If sodium loses 1 electron, it's now isoelectronic with neon. So they achieve stability. So they really, really, they like want to lose electrons. They don't even want to hold that 1 outer electron. So these guys have relatively low ionization energy. Because they have 1 valence electron, they're like, I guess you can take it, because if you do take it, I'll be stable. So they give up their electrons really easily. So when we talk about the trend, as you go from left to right, ionization energy increases. Now, I need to clarify that this is not only because of the number of valence electrons. So let's talk about truly why it increases. As you move from left to right on the periodic table, the atomic radius gets what? As you move this way, the atomic radius decreases. What does that mean? That means that the electrons in the atom are closer to the nucleus. If they're closer to the nucleus, they will be held more tightly, right? The positively charged nucleus and the negatively charged electrons attract. So the closer the electrons get to the nucleus, the more of an attraction they have, making them harder to rip off. So yes, neon has 8 valence electrons, and yes, that makes it stable, but it's mostly because all of those 8 electrons are super duper duper close to the nucleus, making it really hard to want to remove them. Are there any questions about the periodic trend? The periodic trend means left to right or right to left. Okay. What do you think the trend is as you go down a family? So ionization energy. So I'm going to just draw a new, let's see, create form.
Be careful. No. Here.
Okay. All right. So look, we'll just do the alkali metal family. So here's hydrogen, lithium, sodium. Oh, sorry, I'm going to run out of room. Okay, and so forth. So hydrogen, lithium, sodium, potassium, that's all I did. Okay, these are just how many rings they have. Okay, so hydrogen has 1 electron out here, lithium has 1 electron out here, sodium, oh wait, right? Okay, sodium has 1 electron, and then it has all the inner shell electrons. Okay, actually I want to do these in a different color. So 1 electron, 1 electron, right? These all have 1 valence electron. So remember, we're removing an electron. Who do you think now is the easiest to rip the electron off, and why? So, right, ionization energy means we have to remove an electron. So, right, for this one, we'd be removing that electron. 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 Who is the easiest to remove the electron off of, and why?
Go get the bike. Where's your bike? You gonna sit there?
Okay, so hydrogen, lithium, sodium, potassium. So hydrogen is the smallest of these and potassium is the largest, meaning this electron in potassium experiences greater shielding effect. Do you remember what shielding effect is? It's the fact that to get to that, to have the attraction between the nucleus and this outermost electron, there are all of these electrons, okay, in the way, blocking the nucleus to be able to attract this outermost electron. So if this electron is the least attracted to the nucleus, it is easier to remove it. Well, what is easier to remove it? Well, what does it mean if something is easier to remove? It has a lower ionization energy. It doesn't require a lot of energy to remove it. Okay? As opposed to, let's say, hydrogen, whose electron is super close to the nucleus, meaning this nucleus, this positively charged nucleus, and this negative electron are very, very attracted to one another, meaning hydrogen is not going to give up this electron as easy. So this is a higher ionization energy, which means for the trend, as we move down the periodic table, oops, oh, it's not letting me comment on here.
No.
Ionization energy is decreasing. Whoa. Decreasing. And the reason that is because of the shielding effect. The atoms get bigger, the electrons are further away from the nucleus, which means they're held more loosely. They're easier to rip off. Okay?
Stop it, bud.
Oops. So if I go back to the notes, this is exactly what this is saying. As you move across a period, the atoms get smaller, and because they get smaller, the valence electrons are held more tightly, and they're harder to remove. What's up, Nathan?
I only see the periodic table.
Well, I'm not on the periodic table right now. I'm on the notes.
Yeah, but I can't, like...
This periodic table?
Yeah, it was stuck on that for some reason.
Oh,
Hey, Maria.
sorry. Are you on the, I'm going back to the notes though, okay?
Yes.
Okay, so this was supposed to be ranking, and it looks like it says rank by increasing first ionization energy. Sorry, the formatting's a little bit off. Okay, so rank by increasing first ionization energy. So what does the word increasing mean? It means low ionization energy to high ionization energy. So I'm going to refresh my periodic table, and I'm going to circle where all of these are. Okay, so sorry, I gotta get my periodic table pulled up. close, open, new. So if you guys can tell me, since I'm not, or I guess I could look at it. I was gonna say, could you tell me just which ones we're doing? I know argon's on there. Argon's on there. Who else is on there? Sodium, magnesium, potassium. Okay, so sodium, magnesium, potassium. So we want low ionization energy to high ionization energy. All right, so low ionization energy. So again, you need to remember what this means. This is easy to remove the electron. All the way to high ionization energy. This would be the hardest to remove an electron. So these three elements, sodium, magnesium, and argon, are all in the same family, or all in the same period, okay? This guy is one period below it, which means its valence electron is the furthest away from the nucleus, and the further electrons away are from the nucleus, the easier they are to remove electrons. So potassium has the lowest ionization energy. It's the easiest to rip off potassium's valence electron than anybody else on here. Potassium is the lowest. Who's the next lowest? Well, these all have 3 rings of electrons, but sodium is the biggest of the 3, so its valence electrons are further away from the nucleus. And then magnesium is smaller than sodium, and then argon is the smallest and only has 3 rings of electrons, so its electrons are the closest to the nucleus, which make it the hardest to remove. There is their rankings. Questions on ionization energy? Okay, so now you're going to kind of look at this funky little trend, all right? So there are some exceptions in our ionization energies, all right? So as you go across, this is period 1, this is period 2, this is period 3, and then it kind of stops at calcium, period 4. So like as you go across a period, ionization energy increases generally. As you go across a period, ionization energy increases generally. So you go across a period, ionization energy increases. So this is period 1, period 2, period 3, period 4, right? Periods are rows. Except you'll see some little sad dips, exceptions. So let's talk about the exceptions in our periods. Okay, so I would like you to take a moment and I would like you to do the electron configuration for boron and oxygen. You can do noble gas notation if you want. Oops, I'm sorry, this is, whoa, this should be a 2s2. Okay, so let's talk about this in terms of orbitals. I'm going to draw my orbitals just for my valence shell, okay? So this is my 2s orbital, and then my p's look like this. I'm just doing my valence shell. I'm ignoring my inner shell electrons, because remember when we're messing with electrons for right now, we're messing with them from the valence shell. So I'll throw my electrons in there for boron. 1, 2, 1. Okay, and you go, okay, so beryllium would be the one right before boron, He2s2. Okay, and then what would nitrogen be, which is right before oxygen? He2s2, 2p3. Okay, so you'll see that it's actually, so this is boron right here, right now. Okay, and you'll see that there's a little dip in ionization energy, meaning it's actually a little bit easier to remove boron's valence electron than it is beryllium, even though boron is smaller than beryllium. Anybody want to guess why? So I'll tell you this one, and maybe you'll be able to guess the next one. Beryllium looks like this. It has a full shell right here. We know that full shells and half full shells are fairly stable, right? So it really does not want to give you an electron. But boron has this one lone electron in the p orbital. The 2p orbital, I would write this, is shielded or blocked by the 2s orbital. And because there's a little bit of shielding that goes on here, it's a little bit easier to pluck this one electron off of boron. Okay? So that's why there's a dip here. Boron's actually lower in ionization energy than beryllium, so it doesn't really follow our beautiful trend as we move from left to right across the second period. So now let's take a look at nitrogen and oxygen. So here's nitrogen, 2s2, 2p3. What do we know about a full and a half full shell? Well, this is nitrogen, right? Right now it's nitrogen. Okay. And we know that nitrogen, this is pretty stable, half full right here and full right here is stable. So this is nitrogen, pretty stable. And then for oxygen though, we do this. There's one extra electron there because it's 2p4. So now this is oxygen. So what do you think is the reason that oxygen, what do you think the reason oxygen has this little dip in ionization energy? Well, that is because of repulsion in the 2p orbital, specifically right here. These guys don't really want to be next to each other. I mean, they have to be because you pair them up, but because there's this little bit of repulsion right here, it's this electron that I've introduced for oxygen is like, oh, sure, I'll be happy to be removed because then I won't be being repelled by the other guy in my orbital. So you see these are exceptions to our trends.
Stop.
Okay, now the same pattern happens for aluminum and sulfur because aluminum is in the same family as boron and sulfur is in the same family as oxygen. So it's for the same exact reason, but now we're dealing with the 3s and the 3p. Okay, so yes, as we go left to right in general, ionization energy increases because the atoms become smaller, but there are a few little exceptions. And so we just went over the exception of boron and the exception of oxygen. Okay, so let's talk about valence electrons. So use your periodic table, remember. So again, these are how many valence electrons in each family, ignoring our transition metals, which we're kind of ignoring for a lot of this chapter. So again, sodium has 1 valence electron, magnesium has 2 valence electrons, aluminum has 3. Okay? So now what's going to happen is we're going to talk about removing more than 1 electron. Remember, ionization energy is the amount of energy required to remove an electron. That's called its first ionization energy, to remove 1 electron. And then these are how much energy it would take to remove a second electron, and then a third, and then a fourth, and then a fifth, blah, blah, blah. So look that you'll see these big, they're called jumps in ionization energy. They're called jumps. And what that means is they're taking a really big jump between the energies. So here's the amount of energy required to remove 1 electron from sodium. Now, what do we know about sodium? Well, sodium starts off neutral, like, sorry, I know my rings aren't the most beautiful things. 1, 2, 3, 4, 5, 6, 7, 8, 1. Okay, so this is neutral sodium. So sodium's kind of like, I have this 1 electron. Sure, you can take it. See you later. It doesn't require a lot of energy. 496 is considered low ionization energy. Okay. Now, when I take it, I become sodium plus 1. And I also become isoelectronic with neon, meaning I've achieved stability right? I'm smaller, my electrons are close to the nucleus, I have a full valence shell, I'm fairly stable. So you see a huge jump. Look at this is 10 times as much energy about to try to take another electron, meaning sodium's cool giving you one electron, but it does not want to let you take a second electron. After it loses one, it's achieved stability. It does not want you to take anymore. So if you try to take another electron, it will have a huge jump in ionization energy. Okay, it will take a ton more energy. Okay, so again, these ionization energy jumps are based on how many electrons the element would be okay losing and then where it stops. So look at magnesium. Magnesium has 2 valence electrons. So this is the amount of energy required to take the first one. Why do you suppose it's more energy to take a second one? So I'm going to draw magnesium. This is a little bit harder concept. In fact, this is more of a AP chemistry concept, but I'm still going to teach it to you because I think you guys can get it. So magnesium originally has 2 valence electrons. Okay. So we're going to rip off, right? That's what ionization energy means. We're going to rip off 1 electron. So let's say I take this one out. Okay. This is how much energy I have to put in to rip this electron off the atom. Well, now there's still 1 valence electron left. Why is it harder, though, to rip off this second electron? So this one was the first electron I chose to move, and this one was the second. Why is it harder to rip off the second? Does anybody know? Once you rip off that first electron, there's less repulsion in this valence shell, which means this electron is now held more tightly. So it's a little bit harder to remove the second one. But it's like, okay, I'll let you take my second one. Well, after it loses its second one, okay, there's no electrons in this valence shell. And now this is also isoelectronic with neon. Isoelectronic with neon. Okay, so it's like, okay, I'll give you 1, I'll even give you a second, but now that I've given up 2, I've lost my whole valence shell, I don't want to lose any more electrons. So there's a huge jump between the second and third electron removals. Look at this, was like this doubled, and this was multiplied by like what, 6 times as much work than the first 2. So there's a huge jump because after 2, magnesium is stable. It doesn't want to let you have another electron. So the kind of pattern goes and so forth. Aluminum has 3 valence electron. It'll give you 1, it'll give you 2, it'll give you 3. After it loses all 3, it's stable. It does not want to give you a 4th electron. So there's this huge jump in ionization energy between the removal of the 3rd electron and the 4th electron. So I have these answers. So it says, for which electron will the ionization energy jump significantly for strontium? So you go to your periodic table and you find strontium. And you go, okay, strontium. It's right here. It has 2 valence electrons. So it's like, okay, I'll lose 1, I'll lose 2, and it will become isoelectronic with krypton. So it's okay giving up 2. It's not going to want to give up a 3rd one. So you would see that jump for the 3rd electron for strontium. Okay, the next one is for gallium. So we find gallium. Gallium is right here. It has 3 valence electrons. So it's okay losing 1, 2, 3, but it's not going to want to let you have a 4th. So you'll see the jump on the 4th electron. Now, it says, which should have the largest difference, so this is a different way to word the question, between the first and second ionization energies, meaning the element is okay giving you the first electron, but it does not want to give you a second electron. Okay, so which one of these is okay losing 1 but doesn't want to lose 2? I'll give you a second to try to figure that out. You can send it to me in a message. Yeah, I'm going to give you a minute, and I want you to try to predict which atom has the higher first ionization energy. Remember, first just means to remove 1 electron. So what does higher mean? This is helpful. Higher means harder to remove. So I'm going to give you a second to try to rank these. I'll do magnesium and sodium with you. So magnesium is right here. Sodium is right here. Magnesium is smaller than sodium. Because it is smaller than sodium, it has a higher first ionization energy. It's harder to rip off its electrons because its electrons are more attracted to the nucleus. You try the rest. Okay, so I've put all of the answers on here. Again, the closer electrons are to a nucleus, the harder they are to remove. So I've put which atom is smaller and the reason that it's smaller. Remember, as you go across a period, it's effective nuclear charge that makes something smaller. However, as you go down a family, it's the shielding effect that makes something smaller or larger. Okay, so I should say for the smaller, it's less shielding, less shielding, closer to the nucleus. Remember, the Zeph means effective nuclear charge. This stands for effective, and that Z means nuclear charge. All right, we have one more trend. Okay, so here we go. This trend, electronegativity, is how attracted an atom is to an electron. So for electronegativity on our periodic table, fluorine is the most electronegative element. After fluorine, it's oxygen. After oxygen, it's nitrogen. I need you to remember that. So they're all next to each other. This is the most electronegative, this is the second most electronegative, and this is the third most electronegative. Now, for our electronegativity trend, we will completely ignore our noble gases. Our noble gases are stable. They have a full valence shell. They don't want to lose electrons, but they also don't want to gain electrons. So we're going to say, and this is kind of a lie, but we're going to say they have no electronegativity. Zero. None. Okay? The closer you are to fluorine, the more electronegative you are. Now, again, I told you, obviously, oxygen and nitrogen are more electronegative than, let's say, chlorine or sulfur. You just have to memorize this, okay? And the closer you are to fluorine, the more electronegative you are, meaning the more willing you're able to attract an electron. With our noble gases being omitted from this trend, we're going to pretend like they're not there, okay? Which means as you move from left to right across a period on the periodic table, I'm going to represent electronegativity by En. Electronegativity increases. The reason that is because as you move left to right, the atom gets smaller and smaller and smaller. So it wants to capture, it will capture an electron easier. And then as you move down, as you move down a family, electronegativity decreases. Okay, less and less attracted to electron because the atom gets bigger and bigger and bigger and bigger, and the nucleus can't attract the electron as easily. So again, the easiest way is to remember fluorine as your reference. The closer you are to fluorine, the more attracted to electrons you are. Think about it though. Fluorine has 7 valence electrons. It really wants more electrons. It wants one more electron specifically. Remember, these are your most reactive non-metals. That's because they really want to gain electrons, specifically just one. They only need one electron to become isoelectronic with their respective noble gas, all right? So you will see like your halogens gaining electrons while your alkali metals lose them, and often they lose them and gain them from one another, and we'll talk more about that later when we get into bonding. So again, and then the closer the electrons are, the smaller the atom, the more attracted to the nucleus the electrons can be because the nucleus is closer to them to be able to hold them tighter and attract them more. So again, these are the trends right here. So we're going to rank by increasing electronegativity. So low electronegativity to high electronegativity. Oops. So low attraction to electrons to high attraction to electrons. So low attraction. So let's see, we've got potassium, chlorine, zinc, neon. So I'm going to go back to my periodic table. So potassium, chlorine, zinc, neon. Who has the lowest electronegativity? So this first one should be easy. Who is not attracted to electrons at all?
Neon.
Good. Neon, right? It's it's a noble gas. It doesn't want to lose electrons. It doesn't want to gain electrons. So it has the lowest. In fact, we'll literally call it zero electronegativity. All right. Who is the next least attracted to electrons? So in terms of things, these guys have 4 rings of electrons, meaning between these two, these guys' electrons are furthest away of the nucleus, okay? So it's not going to be chlorine. So between these two, though, whose electrons are the furthest away from the nucleus? Potassium or zinc's? Potassium is the largest between potassium and zinc. It has less protons in its nucleus, so it's not going to be as attracted to electrons as opposed to zinc. Potassium has 19 protons in its nucleus. Zinc has 30, so zinc has higher electronegativity. And then we only have 3 rings of electrons in chlorine, and chlorine has 7 valence electrons. It's super close to fluorine, so chlorine has the highest electronegativity of all 4 of these. All right. So if you look at here, this is just another representation showing that as you move across towards fluorine, the more and more electronegative you get, and then you see your noble gases just completely omitted from this trend. We're going to say they have 0 electronegativity, so we'll focus on everything else. Notice it's funky in your transition metal block, which is why we don't pay attention to them all that much. I mean, relative, we can do some things, but we don't pay attention to them all that much. And these numbers down here are actual electronegativity values, which will come in handy in our next topic after break. Okay. I am not doing this. I'm finished with notes for this chapter. So I know there's like 10 minutes left of class. You can go start working on your homework. I will pull this up.